My name is Jahan Marcu, and I'm currently a graduate student at Temple University, although I am acting as an individual and do not represent Temple University. I'm speaking as an individual scientist. My project for my thesis is characterizing the cannabinoid receptor as well as the requirements for different classes or types of cannabinoids to bind. We have indole derivatives like the JWH and WIN compounds. We have tricyclic cannabinoids like THC. There are also bicyclic cannabinoids, and there are the fatty acid amides, the endocannabinoids like anandamide and 2-AG. Well, there are several things that I am interested in, is understanding the history of the plant and how it's evolved over time, as well as compounds that we discover on the plant, compounds that we create, how do they interact with the receptors and what are their requirements for interacting with the receptors. And that is one of the steps towards characterizing the endocannabinoid system. What do I mean when we're studying the structure and function of the cannabinoid receptor? We're studying it on the molecular level. We are like molecular locksmiths, and the cannabinoid type 1 receptor or the type 2 receptor are like locks, and the scientific community has developed many different keys for those locks. Many of the keys fit in the lock, but not all of them can open it. And I speculate that many of these keys may change what's behind the door. You may be able to use a different compound at the same receptor to elicit a specific effect.
So it's like there's actually different locks within the same receptor?
Yeah, they're, much like a lock has grooves in it. The receptor has grooves and pockets where things can fit into it. But the scale is much different. A compound is very, very, very small compared to a receptor is very, very big. And so if you were to watch this in real time, it'd be this tiny little compound in this big receptor trying to attach to a few amino acids. So when you see something like that from our simulations that are generated from our collaborators, you can see the potential for different compounds to be developed in different places for them to activate.
And so when you say doors, do we know what's behind these doors?
We know what's behind some of the doors. For instance, we can talk about pain, anti-pain effects being behind those doors, causing apoptosis.
That's cell death, right?
Cell death. So in cancer, causing cell death is important. So apoptosis is a very specific form of cell death. So cells can die from toxicity. That's not apoptosis. Apoptosis is triggering a self-destruct mechanism within the cell. And that's a very important distinction to make. So chemotherapy agents can just kill cells through cytotoxicity, through necrosis. However, to actually tell the cells that, hey, you know what, you're misbehaving, it's time for you to go, that is apoptosis, and the cells destruct from within to disassemble themselves, and those components are usually recycled by the body.